We'd like to thank Nord, makers of NordVPN, for supporting PBS. Hey everyone, just letting you know that there's new limited edition merch at the merch store. More info at the end of the episode.
All particles belong to one of two large groups. Fermions, like protons and electrons, which make up everything we consider matter. While bosons, like photons and gluons, transmit the fundamental forces. And that about covers the universe, matter moving through space and time under the action of forces. But what if we could create particles in between these two possibilities? Well, physics says that these neither matter nor force anyons can possibly exist, and they may have some pretty incredible uses. We live in a conveniently simple universe. Two particle types, bosons and fermions. But what if there are actually infinitely many particle types? To see how this might be true, let's first do a quick recap on fermions and bosons. The most obvious behavioral characteristic of fermions is that they can never be in the same state as another fermion. If two electrons are spinning in the same direction and you bring them close together, there'll be a sort of force that repels them. This is known as quantum degeneracy pressure, or just quantum pressure, and it's the reason you don't fall through the floor. Bosons, on the other hand, have no problem being in the same state as another boson. They can pile up, and this is the reason light beams can pass through each other and that lasers are possible. But why can bosons share a state while fermions can't? Well, we explained this before in terms of the relationship between particle spin and the exchange symmetry of the wave function. And that's a great video to watch after this one, by the way. The short version is that swapping identical fermions introduces a phase shift to the combined wave function, putting the swapped wave function perfectly out of phase with the original. That means if both fermions are in the same state, then a superposition of swapped and unswapped wave functions cancel out, causing the wave function to vanish. Quantum mechanics forbids this. So instead, a type of force appears to arise preventing fermions from overlapping. That's our quantum pressure. On the other hand, swapping a pair of bosons leaves the combined wave function unchanged, so you could have a superposition of pairs in the same state without any problems. The final part of that frankly awesome video was that we can connect the spin of particles with this exchange symmetry. But you'll have to watch the video for that because I don't want to have to take my belt off again. This connection to spin comes from bringing Einstein's relativity into the picture, and it was discovered by Wolfgang Pauli in 1940. Fermions had antisymmetric exchange symmetry and half-integer spin like half, 3/2, 5/2, etc. Well, bosons have symmetric exchange symmetry and integer spin, so 0, 1, 2, etc. This story about what happens when you have particles swap places is the standard explanation of the difference between bosons and fermions, and for the cause of quantum pressure. It's also roughly reflective of the way that these particle types were discovered in the math. But there's a bit of a problem with this explanation. The whole idea of swapping particles is pretty ambiguous. We showed moving two particles together and through each other, but there's a fundamental quantum limit to how precisely we can track the positions of the electrons. So what if the particles came extremely close and then retreated? Because the particles are indistinguishable, it's not possible to tell the difference between particles passing by each other to swap places versus an extremely close approach and then a retreat. In fact, it's not reasonable to even assign labels that remain fixed to an individual electron. And this is exactly why in 1977, John Magnalinus and Jan Merheim set out to find a new way to think about fermions and bosons that took seriously the fact that naming electrons is silly. And they succeeded, and in the process discovered a brand new type of particle, anyons. Let's go back to our example of two electrons moving towards and through each other. We'll make it easy by pretending that this is a one-dimensional universe. The line that the electrons move on is the only space that exists. That means we can describe their positions with one variable each. Every point in this plane represents a combination of locations for the two electrons. But we just said that we shouldn't go around labeling electrons. In this space, it's clear how to avoid that. For example, this point here has electron 1 at position 1 and electron 2 at position 2, But that's the same physical situation as here, where electron 2 is at position 1 and electron 1 is at position 2. In fact, this whole upper half of the plane is an exact duplicate of the lower half, so let's delete the upper half from our space. This is what we call the configuration space for our two electrons. Every point represents one possible configuration for our system. Maybe say the electrons begin here, but then they both move in different ways to each other, and as they move, the configuration changes, tracing a line through configuration space. But what happens if this line reaches the diagonal border of this space? This represents the particles getting so close to each other that we lose track of which is which. They could have continued on passing by each other, which would look like this line if we hadn't eliminated that whole region, or they could both have been deflected like this. As far as our indistinguishable electrons are concerned, these two paths have to be thought of as the same thing. That means this trajectory is the same as this trajectory, so we only keep the part that's inside our configuration space. So it seems this boundary has a very particular effect on the motion of our two-electron system. It causes it to bounce back. Now, because we're trying to do quantum mechanics here, we need to think in terms of the wave function, not particles. So what happens to the wave function at the boundary? The wave function in quantum mechanics represents the distribution of probabilities for quantum properties, in this case, the positions of the electrons. As the name implies, the wave function is wavy. It's a spread out thing in which the value at each point is influenced by the values at neighboring points, and the whole thing moves around over time according to the Schrödinger equation. We can learn a lot about the two-particle wave function by requiring that wave function to give zero probability on the other side of this boundary and to reflect the wave function at the boundary. The types of wave function that satisfy these conditions get reflected perfectly by the boundary, but with one important change: they pick up a phase shift. Okay, first let's look at a more physical analogy. When light bounces off glass or the surface of water, its phase is shifted by a half a wave cycle. That's a phase shift of pi radians, 180 degrees. We can write this as the photon's electromagnetic field multiplied by e to the power of I times the phase shift. From now on though, we'll define the phase shift as the number of half wave cycles that the phase is shifted. So e to the power of I times eta, where the Greek letter eta is that number of half cycles. So we'd say that light gets a phase shift of 1 when reflected off a mirror. 1 times pi is a half wave cycle shift. The wave function of our pair of electrons also gets a phase shift when it bounces off this abstract boundary in configuration space. And that phase shift is also 1 for the electron pair and for any fermion pair. In quantum mechanics, a phase shift is also applied to the wave function by multiplying it by e to the I times pi times that shift. E to the I pi times 1 is Euler's identity. It's equal to -1. So the combined two-electron wave function gets a minus sign on reflection. And this is exactly the same anti-symmetric quality that we talked about in the previous video. Swapping electrons flips the sign of the wave function. But this new way of looking at it is arguably better because it explicitly accounts for the fact that we don't know which electron is which after their close approach. And this also works for bosons. In their case, the phase shift at the boundary is 0, and e to the I times 0 is 1. That means the boson pair bounces in configuration space with no change. That's equivalent to our particles being symmetric on swapping the particles. Okay, so we've recovered the basic behavior for bosons and fermions without pretending we can tell one from the other. But something new and a bit worrying comes out of this argument. We know what the phase shift has to be for bosons and fermions, but are these the only phase shifts allowed? Back to the example of light. It's possible to build a mirror that causes literally any phase shift you want in the reflected light. So could there be a wave function that experiences a phase shift that's not 0 or pi at the configuration space boundary? Well, actually, yeah. In fact, it's possible to come up with wave functions that have literally any phase shift, any at all, and a particle with a phase shift of anything but 0 or pi is called an any-on. For bosons and fermions, the phase shift or symmetry on exchange is related to their spin, and the same would be true of anyons. That means anyons should be able to have any spin, not just half or full integer spins. So, if this is supposedly a more robust method for understanding particle statistics and it predicts any conceivable spin, why does this universe only seem to have bosons and fermions with their very limited allowable spins? Actually, this prediction that I just described for the existence of anyons is probably right. They should exist in the situation I described, a one-dimensional universe. So let's add some dimensions and see if anyons still exist in those universes. If we have two electrons moving in 2 dimensions, we would normally need a 4-dimensional configuration space, that's 2D for each electron. But we have a trick to get around this. We only care about the locations of the electrons relative to each other, so imagine our axes move around with the electrons. All we need is the distance between the electrons and their orientation with respect to each other. We call this center of mass coordinates, and it gives us a 2D configuration space for our 2 electrons in 2 spatial dimensions. This is what it looks like for the electrons to move around in real space and this new configuration space. Distance between them gets smaller and the configuration moves towards 0 separation. And also the position of the center of mass rises. Once again, the indistinguishability of the particles means some of the new configuration space is redundant. Whenever they pass through 0 separation, we don't know whether they passed by each other or deflected back the way they came. This has the effect of eliminating half the plane because we can never tell which particle is to the left or to the right. But oddly enough, when the configuration reaches this border, it doesn't quite bounce back, rather it Pac-Mans to the other side. In this case, to be able to describe continuous non-Pac-Man-like motion, we have to do a little arts and crafts. We fold the remaining half of the configuration space to join at the edges. Now that same motion in this space looks like moving around a cone. If our 2-electron system makes one circuit around the cone, it means the electrons must have passed the Pac-Man boundary, so they must have passed very close to each other, so we lost track of which is which. This is the equivalent of bouncing off the boundary in the 1D case. It also means that the 2-particle wave function picks up a phase shift as it does this. If our particles are anyons, that phase shift could be anything. If we want to reverse that phase shift, we just have the system retrace its steps. If the phase shift for a clockwise motion in configuration space is some value eta, then the shift for an anti-clockwise shift must be minus that, minus eta. This has to be the case because rewinding things should subtract the phase shift that was added. For the 2D case, that phase shift can be anything we want, therefore 2D anyons should exist. Okay, so what about a universe more like our own, with 3 spatial dimensions? If we have 2 particles moving in 3 dimensions, we need a 6-dimensional configuration space to represent it. And even with tricks like center of mass coordinates, we still have a 4D space, which isn't going to be easy to represent on your 2D screen. What we can do instead is restrict our particles to a 2D plane in that 3D space. If we do that, the configuration space looks just like our previous one where the actual universe was 2D. But there's a difference in the case of the 2D plane embedded in a 3D universe compared to an actual 2D universe. See, in a 2D universe, you can't see the plane of motion from any other direction. But in a 3D one, you can. And believe it or not, it's your ability to do that that ultimately makes anyons impossible. What do I mean by that? Remember the configuration space for the 2D universe, the cone. Motion around the cone introduces a phase shift, and motion in the opposite direction introduces the negative of the same shift. In the 2D slice in our 3D universe, that should be exactly the same. Pass 2 indistinguishable particles through the same point, and they pick up one phase shift. Pass them backwards, and they should pick up the negative to return to their initial state. In configuration space, the 2D slice of our 3D universe should give opposite phase shifts for clockwise versus counterclockwise motion. But now that we're in 3D space, we can do something that we couldn't in 2D space. We can rotate our point of view in the new dimension. Think of this as like looking at a transparent clock from the front and then looking at it from the back. Clockwise will look like counterclockwise, even though the clock itself is moving in the exact same way. If we change our reference frame by rotating it 180 degrees, the motion looks different, as though reflected in a mirror. Now, if we construct the configuration space with respect to our new perspective, we see that motions are reversed. Clockwise becomes counterclockwise and vice versa. But this time, we reverse the apparent particle motion by changing our frame of reference, not by moving the particles differently. So really, there should be no difference to the phase shift compared to previously. But why should the quantum nature of electrons care about which way we are facing? After all, two observers could be facing different directions and should observe the same phase shift. On the other hand, if we really did cause those particles to reverse their path, we would have counterclockwise motion on configuration space, and we would expect a negative phase shift. So it seems we have a contradiction. How can this clockwise or counterclockwise motion both give opposite signed phase shifts and also have the same size phase shifts? Well, they can't really, but the only valid answer is if the ultimate effect on the wave function is the same, because then there's no way to distinguish why the rotation direction flipped. Remember that the effect of a phase shift on the wave function is to multiply that wave function by e to the power of I times pi times the shift. But e to the power of I times pi times eta is not equal to e to the power of minus I times pi times eta. That is, unless eta is an integer. Then the effect of a positive or negative shift on the wave function is identical. Any even integer, 0, 2, 4, or minus 2, minus 4, etc., leads to multiplying the wave function by 1, and these are bosons. Every odd integer, 1, 3, 5, minus 1, minus 3, etc., multiplies the wave function by minus 1. Those are our fermions. So long story short, in a 3D universe, the particle exchange symmetry has to work the same no matter the orientation of the system or the observer. That allows only phase shifts that are multiples of pi, which in turn translates to only bosons or fermions, depending on whether it's an even or odd multiple. Any other shift is disallowed because it breaks the universe, which means anyons can't exist in any universe with 3 or more dimensions. But in a 1 or 2D universe, there's no way to view the particle motion from a different orientation in a way that reflects clockwise to counterclockwise. Therefore, non-integer shifts don't break anything, and anyons are possible. So what is the use of all this? Well, besides being a beautiful explanation of the origin of bosons and fermions, perhaps it does allow us to make anyons in this universe after all. Just last year, a team in France figured out that if you stick very specific alloys together, the electrons in between them are sort of trapped, and they can only move through the 2D surface where the metals touch. Then, by carefully applying magnetic fields, they can give these particles more or less spin than what they should normally have, and as a result, they behave like anyons. This team even managed to move the anyons in specific directions and make them collide with each other, and by analysing these collisions, they were able to prove that the anyons had a spin of a third instead of the usual half for electrons. Anyons could also be useful in quantum computing. Quantum computers work by controlling the flow of probability between two possibilities, but with anyons, probability can flow in more directions, allowing quantum computers to do more complex algorithms, or even store quantum information in ways that are more resistant to noise. We know that all of this is possible, but we are still years away from a quantum computer based on anyons. And there are many other potential applications besides these. Nature intended to give us only fermions and bosons to work with, but by looking very closely at how probability behaves in lower dimensions, we were able to find a treasure trove of infinitely many particles with strange properties. They cannot exist without our help, but we are now learning how to promote these strange lower dimensional entities up into our 3+1 dimensional spacetime.
We'd like to thank Nord, makers of NordVPN, for supporting PBS. Nord's mission is to make the internet better than it is today, free from threats and surveillance. If you've never used a virtual private network, Imagine VPN as an encrypted tunnel for online traffic to flow. Nobody can see through the tunnel and get their hands on your internet data. And with Nord's threat protection, users' clicks are guarded while browsing. If you're downloading a file, threat protection checks it for malware. If you're clicking a link, threat protection checks if it leads to a suspicious website. And in addition to its security features, threat protection also stops many types of web trackers to protect your privacy. To learn more about NordVPN, just check out nordvpn.com/spacetime. 12 years ago, on July the 4th, 2012, the Atlas and CMS collaborations announced the discovery of a new particle to a packed auditorium at CERN. It was revealed to be the Higgs boson, the particle that makes the existence of matter and interactions as we know them possible. To celebrate the fireworks of that collision, we've designed our very own limited edition UV glow print Higgs t-shirt and hoodie. Both the t-shirt and hoodie are UV charged, so after being out in the sun, they'll begin to glow. Because of the UV printing process, we're only able to print a limited number. If you'd like to receive your shirt before July 4th, then you need to put in an order by June 23rd. Check out pbsspacetime.com/shop to see them. There's a link in the description.